So today we will start to design beam under the effect of biaxial moment. I'm sorry, what is the difference? Okay, if you have a beam which is horizontal, supporting another beam, so that the other beam will be horizontal also. And the weight of the beam, the live load, are vertical. So bending moment diagram on this beam will be WL squared divide 8, for example. This moment will be mx or m ultimate x, because here is the x-axis for this beam. This m ultimate x must be smaller than or equal phi mn. This mn will be mnx. What will happen if you have rafter or sloped beam? So this sloped beam is supporting another beam. This is the case if we have purlines. You have a rafter like a frame or truss, whatever, inclined, sloped. So if you are supporting another beam on this sloped surface, this cross section will be inclined like this. What is the issue? The issue is any applied load must be vertical, because the weight of anybody in this world is vertical. The life load is vertical. So your load will be vertical, but the beam is tilted. What is the problem? No problem. Your moment, which is WL squared divide 8, will be divided to two moments. One called M ultimate about x-axis, one called M ultimate about y-axis. Because we have here is the x-axis of the beam, here is the y-axis of the beam. Because the load does not matching with y-axis, like the first one, here is the x-axis, here is the y-axis. The load is matching with the y-axis. But in this case, no, we have angle here in between, this angle theta, which equal the inclined angle for the rafter. That means we will have two components of moment. M ultimate x will be M ultimate, which is W squared divided 8, cosine theta. M ultimate y will be M ultimate sine theta. So we have, in this case, something called biaxial moment. The beam, which has two axes, x-axis and y-axis, will be under the effect of two biaxial moment, mx and my. Why this happen? Because this beam is supported by another beam, and the another beam is inclined, is sloped with angle theta. So the beam does not match with the x and y axis, or the applied load do not match with the x and y axis. It's very simple, very easy for calculation, but you need to understand this point. If we have rafter and we have purlin, this purlin will be tilted by angle theta. This angle theta equal the angle for the rafter. So go ahead and find your ultimate moment, WL squared divide 8. This ultimate moment can be broken to two components, M ultimate about x, M ultimate cosine, M ultimate about y equal M ultimate sine. Because we have two moments, one about x, one about y, we will use the interaction equation to figure out this beam is safe or unsafe. So M ultimate x divided by phi mnx plus M ultimate y divide phi mny these two terms together must be smaller than or equal 1. Just to make sure, if the two terms equal 0.9, 0.95, 0.99, it will be safe and economic. If the two terms 0.4, 0.3, 0.1, it will be safe. I'm sorry, it will be more safe, but not economic. That means you are using bigger cross section. You can make it smaller. We would like this term plus this term to be smaller than 1 to be safe, and very close to 1 to be economic. Okay, one more thing. We understand Mn equal F yield times Z. If you go back to previous week, last week, Mn, the nominal moment, equal F yield times Z. If you would like to get Mn about X, okay, F yield times Zx. If you would like to get Mn about Y, F yield Zy. If you would like to get the design moment phi Mnx, okay, use phi equal 0.9. Phi Mny, go ahead and use phi equal 0.9. So this information will help you to figure out the denominator for this equation. Mnx F yield times Zx. Mny F yield times Zy. Phi will be 0.9, so I can figure out the denominators. The numerators coming from loading. First step, I need to figure out M ultimate, W squared divide A. Then, by using this angle theta, I can figure out the M ultimate X and the M ultimate Y. Then I can set up this interaction equation to figure out the two terms are less than 1. Let's do it by this example. We have truss. Roof system consists of trusses of the type shown in the figure below, spaced 15 feet apart. This truss is repeated every 15 feet, which is S, spacing between main system. So guys, can you tell me what is the information behind 15? I think that means your purlin span will be 15. That makes sense? Go back to this one. If I'm telling you the spacing between this main system and the next main system, which is S, equal 15 feet, that means the span for this beam, which is supported here and supported there, will be 15. That makes sense? So keep in your mind that the spacing between main system is represent the span of the purlin. If this span is too much, the span, I'm sorry, if this is spacing too much, the span of the purlin will be too long. Okay, so be careful about this choice. Anyway, so the trusses spaced 15 feet apart, purlins are to be placed at the joint and the midpoint. For any reason, we don't care about this point right now, we put purlin at this joint and in between. We don't like this. We cannot support purlin directly on the member, but anyway, this is the problem. We don't care about this. The total dead load including on weight of the purlin equal 21 pound per square feet. The life load value 21 also pound per square foot. Steel A36, so the F yield of steel equal 36 kb per inch square, KSI. And select a W shape for the purlin. We have a mistake here. F yield not 50, it's 36. I'm sorry, because the steel is A36. Okay, first step, I will start with loading. From the information given, I can figure out that the span of the purlin is 15 feet. Then I can say each purlin is supporting from this center line to this center line. So what is the value of W dead load? It will be 21 times horizontal spacing 4 times 15. So this distance is 15. This distance is 15. This distance is 15. This distance is 15. So the distance between each purlin will be 7.5. So I believe this distance will be 7.5. That makes sense? Do you agree? If you have any issue, let me know. The problem saying this, we have purlin at the midpoint of the member. It's not the common case, but the problem saying this. So if you can measure the distance between this point and this point, it will be 7.5. So what is the value of W life load? It will be 21 times. What is the spacing? What is the distance here? And what is the distance here? I think the distance for life load will be the horizontal distance, 7.5. But for life load, for dead load, I think we can assume it's 7.5 also. It should be the inclined distance. It will be very close. Anyway, so what is the value of life load? What is the value of dead load? 157.5, 157.5 pound per foot. Pound per foot. Okay. What is the value of W ultimate? 1.2 dead plus 1.6 life. So multiply this one by 1.2 and this one 1.6, 441 pound per foot. So we have dead load here. We have ultimate load here. W ultimate equal 441 pound per foot. That means the M ultimate equal W ultimate L square divide 8. W ultimate times 15 square divide 8. This number will be 12,403 pound foot. I think this is the best time to convert this one to kb. 1, 2, 3. It will be 12.4 kb foot. Probably you can convert this one to kb. Anyway, so M ultimate for this purlin equal 12.4. Because this purlin is supported by these members which are inclined with angle theta here, so this M ultimate can be broken to M ultimate X, M ultimate Y. M ultimate X equal M ultimate, which is 12.4 cosine angle theta. M ultimate Y equal M ultimate sine angle theta. What is the angle theta? Okay, go ahead by using these triangles. This triangle has a total horizontal length 30, vertical distance 10. I can figure out this angle. So the angle theta will be inverse 10. 10 divide 30. It will be 18.4. So this angle will be 18.4. This angle will be 18.4. So the final values for M ultimate X will be 11.7 kip foot, 3.9 kip foot. So right now, I am done with the numerator. M ultimate X, M ultimate Y. Piece of cake. Piece of cake. One more time. From loading, each purlin is supporting from center line to center line. So what is the distance? This distance will be multiplied by dead load, which is bound per square foot, and the live load, which is bound per square foot. So I can convert this surface load to distributed load. Next step, I need to convert this dead load and the live load to be ultimate. So I have to multiply dead by 1.2, live by 1.6. So the final conclusion, we have simple supported beam with a span 15 feet under the effect of W ultimate 441 pound per foot. The bending moment diagram for this simple beam will be WL squared divided 8, equal this number, 12.4. But this moment does not matching well with the axis. Why? Because this purlin is supporting by tilted or sloped members. So the case right now, this moment will be broken to two components, M ultimate X and M ultimate Y. Next step. Mn equal F yield times Z. So we need to start to assume selected purlin. I need to go to my tables and go ahead and select a cross section. It's a trial, so let's do okay, let's do W18 by 50. This one. You will ask me, why this one? I don't know. I selected anyone. I don't know. So I will assume W18 by 50. I will try by this one. So this cross section 18 by 50 has Zx equal 101 and Zy equal 16.6. Okay, that's good. So if you would like to get phi mnx, phi 0.9. To get mnx, okay, go ahead and multiply F yield times Zx. So 0.9 times 36 times Zx 101. What is the value? 0.9 times 36 times 101. This value will be 3,272.4. Please be careful. because 36 is kept per inch square. And Vx will be inch third or cube. So the final answer will be kept inch. Please convert it to be kept foot, because the applied bending moment is kept foot, So these numbers are kept foot. So please keep your units kept foot. I will divide it by 12. Your number will be 272.7 kept foot. Okay. The other term, phi MNY, phi 0.9, F yield 36, Z Y 16.6. This number will be 5,307, 537.8 kept inch. Divide it by 12, it will be 44.8 kept foot. I am done with the denominator. The final conclusion, last step, M ultimate x divide phi MNX plus M ultimate y divide phi MNY must be smaller than or equal 1. Let's see. M ultimate x, how much? 11.7. Phi MNX, 272 point something, 0.7. Plus M ultimate y, how much? M ultimate y, 3.9. Phi MNY, 44.8. What is the value? Let's see. This number equal 0.13. Okay. Your conclusion, this number is smaller than 1, you are safe. Actually, you are more safe. And this choice is not economic. Do you know why? Because this number is very, 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 very small. That means you are choosing a huge or bigger cross section. So try smaller one. You remember I told you why you select this cross section? I don't have any answer. I just select one. And I checked it and I found the interaction equation give me a number which is very, very, very small related to 1. We recommend to choose a good and economic cross section, this number to be 0.9 to 0.99 to say, okay, we are safe and we are selecting economic cross section. In your exam, in your homework, you don't need to repeat your calculation. If you are unsafe, let me say unsafe, we need to choose bigger one. If you are more safe, you have to say we are safe, but we need to choose smaller one. You don't need to repeat your calculation, just one trial is enough. Any question about this point? Guys, any question about design of purlin? It's very easy. Very easy. But keep in your mind, if your purlin or beam or anything supported by inclined or sloped member, that means the bending moment, which is M ultimate, must be broken to two components, M ultimate X and M ultimate Y. And that means we have to use this interaction equation to make sure that the interaction components smaller than or equal 1. Any question? Okay, guys, just 2 minutes. I will be back by 2 minutes. Just 2 minutes, okay? I'm back. Sorry, guys. So, to summarize what we learned until this moment, we learned if we have beam, this beam has load, whatever the applied load. That means we have moment. The maximum moment, M ultimate, must be smaller than or equal phi Mn, which is the design bending moment. For purlines, we have a special case because this M ultimate, which is applied on the beam, and this beam is supported by sloped member rafter. So this moment must be broken to M ultimate X and M ultimate Y, two components. M ultimate X equal M ultimate cosine. M ultimate Y equal M ultimate sine. Because we have two components, that means we cannot use this one only. We need to use interaction equation. So M ultimate about X divide phi Mn X plus M ultimate Y divide phi Mn Y must be smaller than or equal 1. This equation can be called interaction equation if you have two components of moment. Does that make sense? I will not say this situation will happen only with purlines. I will say this situation will happen with any beam supported by sloped beam. If you have a sloped beam, sloped roof, sloped rafter, sloped anything, and this beam supporting another beam, so the other beam will be tilted by angle theta. So we are in this situation. The second part in our meeting today, design of column. If you have a steel column, what is the situation? We covered this, if you remember, for trusses. Because compression member is in truss is a column. Because your column, if you have a column like this in any building, it will be under compression P ultimate. So the column can be called compression member. Compression member, the same sequence that we covered before. Exactly. But in your mind, design of compression member that covered before in truss will be the same like design of column. The nominal compressive strength Pn equal F critical FCR time area gross. If you would like to get the design compressive strength, you need to multiply Pn by phi. This phi will be 0.9. That's it. area gross, the gross area of this cross section. If you open your tables for any cross section, for example, we have a column W18 times 50. We have a term here called area. This area is called area gross. The area can be found from a table. What about FCR, F critical, which called critical stress? We have two situations based on the mode of failure. If you have an elastic behavior and KL divide R smaller than or equal 4.71 square root E divide F yield, then F critical equal to this term. The other situation, F critical equal to this term. We covered this before, but just a hint. K buckling coefficient. You remember sometimes your column is fixed, or fixed free, or hinged, or hinged fixed. P here equal 0.7. I'm sorry, 0.5. Here equal 2. Here equal 1. Here equal 0.7. Based on the K factor, and L, the buckling length or the total length of the column, R, Rx or Ry. Anybody remember what is the meaning of R? Radius of gyration. If you open a table for W shape, for section properties, we have here R about x-axis and we have R about y-axis. Which one I'm gonna use? We will use the smallest one, or if we have a different situation, we will cover it. Let's do an example and see how can we use this technique in designing a column. Just a second here. We need to open another file. See the structure. We have steel column, F yield equal 36, KLX equal 40, KLY equal 20. Find satisfactory W12 cross section that can support an axial dead load or axial load 200 kb dead load and 200 kb life load. Do you know what is the meaning of KLX and KLY? Sometimes the column looks like this. Here is the x-axis and here is the y-axis. Let me complete this column here. Sometimes this column is connected by another beam here. Can you imagine? And this beam is continue to the other side also. Like this. You know? Sometimes this is happened, but we don't have something here. We don't have something here. So the situation right now, if this column would like to buckle, it will buckle like this, because this point is supported by this longitudinal beam and this longitudinal beam. But if this column would like to buckle in the other direction, it will buckle like this, because we don't have anything in this direction or this direction. That makes sense? Guys, did you get this point? Yes. Yeah. Oliver, every single information I'm covering in this course or concrete design course or structure analysis are very important in your professional engineer exam. Especially this point. Sometimes you will say, hey, why the column has a length equal 40 feet about x-axis and the same column has another length equal 20 feet about y-axis? Because sometimes we have this situation. Your column is buckled up at the midpoint in one direction and do not buckle up in the other direction. So sometimes this direction will be 20 feet only, but this direction still 40 feet length. So we need to buckle each column in the weak or weakest direction. I think this column is very weak around this direction, so I buckle it to buckle into double curvature. But the other direction is very strong, so I will let the column to buckle in one curvature. So I'm trying only to explain why this information and why this information, because one of you will say, hey, we have one column, so why this length is 40 and this length is 20? Because we have something cause this problem or cause this situation. Anyway, so which length I'm gonna use? KLX equal 40 will be critical, or KLY equal 20 will be critical? Actually, I don't know. I don't know which one is more critical. Do you like to know which one will be more critical? We need to get the full term. This one. KL divide R. KL divide R. Get the value of these two terms, and then I can tell you which direction will be more critical. What is the value of Rx? What is the value of Ry? I cannot figure out the value of Rx or Ry until I assume cross section. Okay, go ahead and assume a column. Please, you don't have full choice or full freedom to choose any cross section. We need to choose 12 times something, because the problem said this. We need to select cross section W12 times something. So I will open the table and search for W12. Here you go. We have many cross section W12. Go ahead and select one of them. We have to select W12 time what? Time anything. Go ahead and assume. What do you like? Okay, let's start with, I have no choice. It's up to you. So I will start with this one. W12 time 120. Let's start. Let's try this one. So 12 times 120. So 120, we have value for Rx. It will be this value, 5.51. And we have value for Ry. It will be 3.13. Okay, go ahead and find K Lx divide Rx, K Ly divide Ry. Your number here will be 40 times 12 divide 5.51. This one will be 20 times 12 divide 3.13. Guys, remember, this value of R and the R are in inch. So this one in inch, this one in inch. But these lenses, KLX in feet, KLY in feet. So I multiply this number in feet times 12 to be in inch. This number 20 in feet times 12 to be in inch. So you can get a number. So your number here will be 40 times 12 divide 5.51. It will be 87.1. The other one, it will be 76.6. The biggest value will be the more critical. I cannot say 40 greater than 20, so I will use 40. No, we have to wait. Probably something will happen. We have to get the value for KL divide R, which is called slenderness ratio. Slenderness ratio, KL divide R. KLX divide Rx, KLY divide RY. Then, based on the numbers, the most or the biggest value will give you the more critical situation. So right now, KL divide R, which will be used, will be 87.1. Okay? Which one? This situation or this situation? I have to wait until to get the value of this term. 4.71 square root E divide F yield. 4.71 square root E 29,000 divide F yield, which is 36. So what is the value? 29,000 divide 36 under square root times 4.71 will be 133.7. I believe KL divide R is smaller than 4.71 square root E divide F yield. So we are in the first situation. F critical will equal this one, 0.658 to power F yield divide Fe, all of them times F yield. Everything we can figure it out. What is the value of Fe? Fe equal this term, pi square E divide KL divide R square. KL divide R square. You will ask me, hey, which KL divide R? We decided which one is more critical. We decided which one is more critical, the biggest one. So, pi square E 29,000, KL divide R 87, I think 87.1 square. So I can figure out the value of Fe pi square times 29,000 divide 87.1 square. This value will be 37 0.7. Go ahead and find F critical. 0.658 to power F yield 36 divide 37.7, all of them time F yield 36. So the value will be 24.13. So Pn or phi Pn equal phi F critical time area gross. Phi is 0.9, F critical 24.13. Area gross, I forget something. The cross section that you assumed has area gross equal 35.2. 35.2. So the final answer will be 764.4 kip. What about P ultimate? 1.2 dead load plus 1.6 live load. The dead load value is 200 kip, live load is 200 kip, you are lucky. Okay, so 1.2 times 200 plus 1.6 times 200. 1.2 it will be 560 kip. So the final conclusion that P ultimate smaller than phi Pn safe. And I think your number 560 is smaller and close somehow to 764. So your cross section, which is W12 times 120, is safe and somehow economic. So to design a column for any structure, for any steel structure, column, under the effect of axial load only, we need to assume cross section. We need to check buckling about X, buckling about Y, and use the biggest value because the biggest cylinderness ratio is the most critical. Then we need to find the phi Pn, which is the design ultimate strength or compressive strength, equal phi F critical area gross F critical based on this situation or this situation, so you can decide, and then we can figure out the value of Pn. The final conclusion, P ultimate must be smaller than or equal phi Pn. Then you can say this assumed cross section is safe or not. Do you have a question?
Yes, sir.
What is your question?
Since P ultimate is close to phi Pn, that makes it safe and somehow economic. But if P ultimate is a lot less than 560, then it would be more safe but not economic. Correct?
Yes. Yes.
Okay. Thank you.
Don't worry if your P ultimate. Don't worry if your P ultimate equal 764 kip and your phi Pn equal 764.4. You are safe and don't worry. You are safe and more economic. 764 is smaller than 764.4. Don't worry. Don't say, no, I need more factor of safety. No, don't consider this. Do you know why? Do you know why? Because 1.2 and 1.6 are factor of safety. The actual dead load on the building is 200. The actual life load is 200. So that should be the actual load is 400. But we took 20% factor of safety extra, 60% factor of safety for life load. That means we took factor of safety previously. So don't be worried if your B ultimate is very, very, very close to phi PN. You're still safe, but make sure that B ultimate is smaller than or equal. The design philosophy said or equal. So sometimes B ultimate is equal. PN, phi PN. That's fine. You're still safe. Don't worry. You're still safe. But doesn't make any sense that B ultimate equal 100 kip and the phi PN equals 700 kip. No, 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 no. That means you are very, very more safe. And that means your choice is not economic. You are wasting money. You know, guys, anybody know how can we purchase steel? Steel is bought by weight. If you go to any producer or anybody to buy some steel stuff, they will not say W20 times 50 with a price and W20 times 70 with a different price. No, I will say the unit weight, for example, 1 pound of steel equal $20, for example. So I don't care what is the cross section you are using, what is the cross section you are buying. My concern is how much weight you are buying. So I will multiply how much weight by $20 to get the final price. So we need for steel, especially if you would like to go to buy gold or mass or something like this, we need to be more sensitive about how much weight you are using. And you remember, smaller section means smaller weight. Because we understand that W20 times 50 and the W20 times 70. What is the difference? Both of them has the same depth, 20 feet, but this cross section has weight 50 pound per foot. This cross section has weight 70 pound per foot. So this one will be more expensive than this one. This one will be more expensive than this one. So when you are trying to design steel member, we need to make sure that P ultimate is it's close to phi PN to make your cross section safe and economy.
Can I ask you another question, Dr. Amy?
Yeah, go ahead.
If PU is 500, or sorry, if phi PN is 500, but your PU is 500.1, since we're talking big numbers and kip, would you say
no. And this case is unsafe. In this case, if P ultimate equal 100.1 and the phi PN equal 100, no, it's unsafe. Unsafe. You have to make sure P ultimate is smaller than or equal phi PN. In this situation, you are more critical, so don't be in this situation. You know, guys, if something happened during the life of the structure, for any reason, for something happened, and the people were killed during any collapse, so we will go back to your calculations. And we need to decide who is responsible. So you are a designer, don't be responsible. Make sure your calculations are clear, following the rules of any standard. AI SCC said P ultimate must be smaller than or equal phi PN. If you satisfy this equation, you are not responsible for any failure, for any collapse. But if you are saying 0.1 is nothing, okay, I can say it's safe, and something happened, probably it's not your issue, it's not your fault, but for some reason something happened. I'm sorry, I will go back to your calculation and I found this little mistake. I will say it's your responsibility. You know what I mean? So be careful about your design. Make sure you are on the safe side and you are following the first priority. You have to follow the rules, the standard. If you are following the standard, you are in the safe side. You are not responsible for anything will happen in the future. Next meeting. So until now, we can design beam under the effect of moment. We can design column under the effect of axial load, P ultimate. Sometimes we have beam column member. I'm sorry. What you mean by beam column? Is it a beam? No. Is it a column? No. It's a combination. The member under the effect of moment and the axial force at the same time. And this is the case if we have frame. If you go back last year for structure analysis, if we have frame, we can draw axial force diagram and we can draw bending moment diagram. For this column, for example, you can find the moment and you can find P ultimate or axial force. So we have a member under the effect of axial and the moment at the same time. This is the case if we have beam column design, which has a member under the effect of bending and the axial compression at the same time. We will use another interaction equation, and I will cover this next meeting.